All right, welcome. This is the first of the water videos, and I'm just going to talk some freshwater ecology here. And there'll be a lot of definitions and words that I'm going to mention, but not spend a lot of time on because I don't see them as a huge part to the exam at the end of the year. And so, limnology is kind of the study of this freshwater ecosystem. Two types of bodies we'll talk about today, lentic and lotic. It simply means standing water. If you hear lentic, lotic is like a lake or a pond. Lotic is like a river or a stream, something that's moving as it goes through. And so on campus here, we've got both of these fairly close by. Lakes, how do they form? Many lakes are formed by some mammals, and that could be humans to make dams to create power generation or to reduce floods. Beavers are also one of the most destructive animals to their ecosystem because they create beaver dams. And so that's this picture here. Essentially a lot of sticks and mud that the beavers have assembled to create a habitat for them to live. And so it's kind of a neat thing. A couple different layers we're going to talk about within a lake. The top layer is the epilimnion, and up here it kind of freely circulates and it'll move around with the wind blows across the surface. It can move that layer along. The metalimnion is the middle, and so eventually as you get down here, there's going to be a really sharp change in temperature, and that change in temperature is called a thermocline. And we saw this with the El Nino discussions that we had earlier. Remember that thermocline was really valuable along the western coast of the Americas because it brought the cold nutrients up from the bottom. And so this metalimnion is where that thermocline occurs. And so the temperature rapidly drops here. We're not getting the solar radiation down through, and it's not cycling around. And then the very bottom is the hypolimnion. This is where kind of our nutrients will collect on the bottom. All right, and then also we have some different zones along the edges of the lake. And so this is kind of our lake shore. The first one of these zones is the emergent zone, and it's titled such because this is where you've got plants growing that are emerging from the lake. And so it's a shallow section. These plants get plenty of sunlight and they're able to grow up through and past that emergent zone. After the emergent zone, you get to the submergent zone, and I don't think these zones are super important to know. The littoral zone is one I would know. This is the area of the lake, right? So if you picture a lake, this is the area of the lake where the light penetrates deep enough to reach the bottom. And so light will only make it through a certain distance of water, and it depends on how clear the water is. A term like turbidity will come into play later on. But let's say the light penetrates that deep. We'll call that 3 meters. Our littoral zone would be where the light reaches all the way to the bottom, where the light reaches all the way to the bottom. That's kind of a bad drawing. But over here you get a picture. This is our littoral zone, and this is where the aquatic plants that need roots can grow. Out here, this is the pelagic zone, where we're going to have the plankton, we can have free-floating plants, but the rooted plants are not going to grow in this area because they're getting no sunlight down here. And so this is the littoral, this is the pelagic zone of the lake. You might also hear this as the photic zone, same thing, and you can see it a little better here. This section, this is the depth that the light penetrates, and so here along this area of lake is where plants have the ability to grow because the light's reaching all the way down to the bottom. We call the one below it the aphotic zone, but again, a lot of these terms here I don't think you're going to need to know, but you're hearing them just in case. This is a picture, right, actual lake, and so you can see this is a very clear water, and so it probably has light throughout. It's probably entirely a photic lake because this looks like some crystal clear water. A couple things. In the summer and the spring, you get a lot of heat on the surface, and so it just kind of cycles along the top here where you don't get anything going down into the thermocline or the hypolimnion, and so you end up with a buildup of dead stuff along the bottom, nutrients and the like. And that's the summertime. When winter comes along, that wind, because it's not a significant change in temperature throughout, that wind is going to drive kind of that big conveyor belt, and it's going to draw nutrients up from the bottom. And this is called overturn. Seasonally, we mix the water. This is very good because it's going to distribute those built up of nutrients on the bottom of the lake to the edges of the lake and allow it to be used then by the plants or by the animals that might live in those zones. Low-tick ecosystems, these are the ones that are flowing water, streams or river right out there. Really important factor is the velocity. How fast does this stream move? And a lot of things that determine the velocity. Here, our St. Johns River, a very slow-moving river, because the gradient, the slope of the river, if you picture a mountain stream, it's got a pretty good slope to come down, and so it picks up a lot of speed due to gravity. Florida is very, very flat, and so the slope of the St. Johns is very small, meaning it's not going to flow very quickly. A couple other things that matter. One of them is the shape of the channel. A very straight stream is going to go much quicker than a stream that is windy, because each of these turns is going to take away a little bit of speed. Streams, again, it's determined by the lay of the land, the roughness of the bottom. Really, the gradient is important. But as it goes, it's going to pick up debris, and so that debris is going to be important later on. It'll kind of bounce and roll, and you've probably seen those nice smooth river rocks before. So it really depends on the area and what's there, but the water is going to move it and kind of smooth everything out. Couple terms to know here. One of them is a watershed. Watershed is where all the land, that water runs off into that common body of water. And so if you picture, this is the St. Johns, right? It flows north, and then it kind of hooks around Jacksonville and goes out to sea. If it rains out here, that water will flow downhill, slight of a hill as it may be, into the St. Johns. Same thing if you're here, right? That water is going to flow. And so the watershed is really important to keep in mind when we're using chemicals or we're having some sort of runoff, because it can move a very long distance to enter a body of water, and you may think, oh, I live so far away from the river, it's not going to affect anything, but actually it possibly could if you live within the watershed. Floodplain is another good term to know. We'll get to turbidity later. This is a strip of land around a river that is dry and flat, but potentially at risk to floods when it's rainy or in the spring when the snow around it melts. And so you might see, if we have a cross section here, our stream, I'll give it a bumpy surface, might be like this, and you've got some surrounding lands, and then there's your mountains on the edge. This land here is great for farming and building houses and stuff like that, but the issue is that is on a floodplain, and so when that seasonal rain or when that snow melts upstream, that water level can rise and cause a lot of problems. And so we build levees, we build dams to help control some of this stuff. There's some natural ways to prevent that as well, but we kind of like the man-made stuff. Couple terms in the stream. We've got a riparian zone, which is where the land and vegetation borders the water. And so if you're looking at a picture of a stream, I've got one coming up, you'll be able to see the riparian zone around it. And then a riffle, this is in the stream where you see white water. There's something there, like usually a rock or a log, causing the water to move around it. And these riffles are important because they're going to stir the water up. They're going to introduce more oxygen into the water and kind of create habitat for animals to live. So here's a stream. This would be an example of a riffle here. You can see a little bit of white water. There's another one right here behind my head. The riparian zone would extend out to the edge of this vegetation, and so it's kind of that strip around the stream of all the plants and stuff growing around it. Some important things for stream chemistry. pH is a very important measurement. We're looking for that neutral pH, somewhere between 6 to 9. There can be synergistic effects with this, and so what it means is if we have something like iron in the stream, that iron can have an increased effect on the animals or the plants living there if the pH drops. And so certain pollutants will have greater effects due to synergism with pH changes. And so the presence of iron might not necessarily be a bad thing, but if the pH drops, that's when it can become an issue. Another really important term of stream chemistry is dissolved oxygen. And so anytime you've got water, this is just a cup of water here, there are oxygen molecules above that water, right? Our O2 molecule is oxygen. And those oxygen molecules are water soluble, so they will dissolve in the water. This is what lets fish live and breathe in the water. Their gills funnel water over them, and they pull out these oxygen molecules. And so the more oxygen you've got in the water, the more aquatic life it can support. The kind of general rule of thumb here is that 5 milligrams per liter is about as small amount of oxygen as we can tolerate for aquatic animals like fish and crayfish and things like that. As it drops further, you end up with fish kills, and you look at all these lumps on the edge of the lake here or the stream. Those are all dead fish due to decreased oxygen. This is, if you remember the term eutrophication, eutrophication eventually leads to the drop in dissolved oxygen, which can lead to fish kills. And so that's one of the ways that dissolved oxygen can drop. Oxygen is much more soluble at cold temperatures, and so the colder the stream, the more DO you have. So temperatures are really important here. And also the faster moving water, more riffles in the stream, the more DO you have. And so if you went on the 9th grade trip to the whitewater rafting, those streams there, cold water plus very fast moving water, means their dissolved oxygen is very high, and they probably don't have to worry about having these fish kills due to DO. Another important thing closely related to DO is BOD. This is not the body spray, this is biological oxygen demand. And so this is how much the organisms use. And so this includes things like fish and insects, but really the important one here is bacteria, because there can be a lot of bacteria and they add up quick using up the dissolved oxygen. Those bacteria are using it for decomposition. So the more dead stuff, organic material in the stream, the more bacteria you have working to break it down. If there's not a lot of oxygen, the decomposers start to die off. Before they start to die off, though, things like fish, the bigger stuff, are going to die. This is a symptom of low dissolved oxygen. You see these bubbles over the fish's eyes. That's where you get oxygen blocks in the blood vessels, and they start swelling up, and this fish is not going to make it, right? This is a very advanced stage of low dissolved oxygen. A couple more symptoms you can see of dissolved oxygen, just real nasty stuff. Here the blood vessel broke from the oxygen clog and is bleeding out through its face. So really disturbing stuff. And that's where we're going to stop for the video here. That's just kind of the introduction to freshwater ecology. Thank you for watching. Please bring some notes to prove that you watched it, and be prepared to discuss on class the next day. Thank you.